think about it, water is the most abundant substance on the planet. You'll find it everywhere. Like, it occupies every single ecological niche you can think of in different forms. It's in places that you wouldn't expect. It's in rocks, it's in the earth's crust, it's in the air we breathe. It's present everywhere. And for a substance that is so important to life, and that is so central to our life and so widely available everywhere, we actually don't know that much about water. Sure, we have extensively studied the water molecule. We know the properties of H2O. We know as a solvent how it operates, and we can predict what will happen if you dissolve something in water. There are a lot of things we know about the water molecule. But water as a substance, which means when water molecules come together to form bulk water or ice, it behaves in strange ways that we haven't been able to explain yet. For example, ice floats on water, and this is our everyday experience, and this is usually put down to something called the anomalous expansion of water, because usually the solid form of any material is denser than its liquid form and has to sink. But water actually expands when you freeze it below 4 degrees. And then there are other things like, why is ice slippery? It's the most common experience for all of us. How does water manage to climb all the way to the top of the tallest trees in the world? It reaches the last leaf and the last branch. It's not just mere capillarity. There are some mechanisms at work that spend energy to raise it all the way up. What about clouds? How do condensed water droplets coalesce and clump together to shape a cloud? And interestingly, why does hot water freeze faster than cold water under some specific circumstances? So water exhibits a lot of mysterious behavior that we haven't been able to explain satisfactorily. There are a lot of models, a lot of theories that try to explain this, but not one successful model that can account for all of them. Now, one other thing that is very critical about water is the structure of water itself. Now, when you think of water, you imagine a lot of water molecules randomly moving around frenetically in a chaotic fashion, bumping into each other. That's kind of true for most of bulk water in a glass beaker, for example. But when water molecules come close together, they begin to socialize in a way. So they begin to hold hands, and they begin to form these structures, these long chained structures that are formed. They form sheets, and then there are layers of sheets, and these are long range. So it's not just like a nanometer or a couple of molecules. They go on. This kind of water tends to exclude particles from it. It's almost like a crystal. So if there's anything that you put in, like dust or anything that's dispersed in it, this kind of water, as it forms a structure, it pushes us out. So a special name was given to this phase of water, which is neither liquid nor solid, called EZ, or the exclusion zone, or easy water. Now, I spoke to one of the world's foremost researchers when it comes to the field of easy water, Dr. Gerald Pollack from the University of Washington. Dr. Pollack and his team have been instrumental in revealing a lot of the properties of this particular phase of water, and he's also the author of a best-selling book called The Fourth Phase of Water, where a lot of these details are laid out. I hope you enjoy this video. Hello and welcome to the channel. Today we have a very special guest with us, Dr. Gerald Pollack, who is a professor at the University of Washington in the Department of Bioengineering. Dr. Pollack, thank you so much for joining us on this discussion.
Oh, it's my pleasure. And it's really an honor to speak with you all the way in India, one of my favorite places.
Oh, nice. So, so the topic obviously is going to be about water and the big discovery of easy water and the fourth phase of water. But before we get into that, since you work in the Department of Bioengineering, could you just tell us what exactly does it mean and how is it connected to water research?
It's not connected.
Okay.
You know, um, you might say I'm an outcast or pariah in the department. Most people in the department do bioengineering. They do engineering work that's related to biology or medicine. And what we're doing is fundamental science, and so it doesn't fit at all. Um, if that's sufficient to answer your first question, I can stop there. There's a lot that I can say, but I can stop there because other material may be more interesting.
Right. And so that brings me to the next question. So how did you get into water research?
Well, okay. That question, the answer to that question requires a bit of development. So if you allow me,
Sure.
I was for years my laboratory was engaged in research on muscles and how muscles contract at the molecular level. You know, the proteins actin and myosin are somehow connected with contraction, and we were trying to figure out exactly what kind of interaction happened to create muscle contraction. And we did that for well, several decades, and the results that we had really set the course of you might say a attitude and approach that followed. Namely, there was a theory that was put forth, and it was put forth by a very distinguished gentleman. His name was Sir Andrew Huxley, and he's a member of the famous Huxley family, and he's a Nobel Prize winner and president of the Royal Society and master of Trinity College, Cambridge, etc. Every distinction that you could imagine.
Is he related to Aldous Huxley, the great Aldous
Yes,
Huxley?
yeah,
Okay.
it's the same family,
Okay.
but he is the only one who won a Nobel Prize. He won a Nobel Prize for his previous work on nerve conduction.
Okay.
So he came up with the theory of muscle contraction, and unfortunately, or fortunately, as you might think, every result that we obtained in the laboratory failed to fit that theory. On the other hand, he was so distinguished that almost every worker in the field paid homage to this great man, this distinguished. And any challenger, it was a real uphill battle. Despite the fact that the results didn't fit the theory, we didn't make much progress. Or I should say, we made progress, lots of progress, but we didn't make very much progress in convincing anybody that something was bankrupt with this theory. And the theory still pervades all of physiology and medicine. This is the way people presume muscle contracts, the way his theory suggested, but it didn't work, and it still doesn't work. And the theory is essentially erroneous. And I learned something from that. I learned that any new idea, new theory is not embraced virtually at all. There's a lot of resistance to it. And I should have known that because throughout the history of science, that's been the case, that new ideas that challenge the old don't generally go too far.
Mm-hmm.
And so that experience colored my vision of how exactly science works. Anyway, there was a gentleman who I picked up at the airport, the Seattle airport, to work in my laboratory. And as we were driving from the airport to my home, where I was going to put him up for a few weeks until he and his wife could find a place to live, he was telling me there's a conference in Hungary. He came from Hungary. And the conference is to commemorate uh, a biophysicist who had been very prominent. And he had two areas of interest. One was water, and the other was muscle contraction. He said, "You should go. You should represent the field of muscle contraction because his ideas were not too different from your ideas about challenging the current view." So I said, "Okay, I'll go." And I presented my material, and I think it was reasonably well received. But what impacted me more than my own presentation were the presentation about water, because like everybody else, I thought, water is H2O and there's nothing more to it. And everything that can ever be known about water must already be known because it's a simple molecule and people have studied it, for centuries. So, but I was taken aback because there I met a scientist named Gilbert Ling who had come to the U.S. From China, and he was talking about water. And he had a vision of water, mostly in biology, that differed from everybody else, or virtually everybody else. And his experiments and his theory said, well, the water that's inside of cells is not liquid water. It is not ordinary H2O liquid. He said the molecules inside the cell are lined up like soldiers at attention. He called it structured water. And I was impressed not only by his theory, but by massive amounts of evidence that he had accrued to demonstrate that he was correct. And not only did I meet and get to know Gilbert Ling, but also I met perhaps a dozen other scientists who had been present at the conference who had evidence to support that point of view. I was blown away by this evidence, and so I went.
And just to, sorry to interrupt you there. So when you
Yes.
mentioned that he said that the water inside the cells were structurally different, so I'd imagine for a common man who, let's say you have a bottle of water in your hand or a beaker of water, you sort of imagine the water molecules to be all randomly moving around, like without any specific direction. It's kind of as liquid. It's just moving around. So
Yes.
the water in the cells are sort of arranged in a regular pattern, almost like a crystal,
Yes.
but not quite like a crystal.
Yes. Exactly. Yeah,
Okay.
like a crystal. Yes. Exactly. And he and other colleagues had lots of evidence to support that. And this is not an idea that came randomly. If you look back at the history, there are other people who had supported that point of view, and one notable one was Albert St. Georgi, and it's not a name that's familiar, a household name, but St. Georgi is considered to be the father of modern biochemistry. He discovered vitamin C, got a Nobel Prize, and he was about as creative as just about anybody. And he's famous for short aphorisms, and one of them related to water and structured water is this. He said, "Life is water dancing to the tune of solids."
Wow.
So he knew about the centrality and the importance of water, and was on the same bandwagon as Gilbert Ling. And there had been some people before that, but Gilbert Ling was the major proponent. So I found myself really intrigued because if you think about it, if Ling is correct, then all of biology needs to change points of view, because the central idea in biology is that water is just ordinary liquid water, and molecules are floating around and they can diffuse, and there's osmosis and whatever. But Gilbert Ling's idea that is it completely different, and so much of biology, if he was right, much of biology would be wrong and needs to be reconsidered. And of
Right.
course, that got my attention because maybe in part because of my experience with mussels, where essentially the whole world is thinking about the model proposed by Sir Andrew Huxley, but it doesn't fit the evidence, so something is wrong. And here again, here is something that doesn't fit the evidence. I mean, the common view that your cells are filled with liquid water doesn't fit the evidence, and Ling had evidence to suggest otherwise. And just as an aside, if you want to demonstrate really easily that the water inside your cells is not liquid water, all you need to do is take a razor blade and cut yourself. If you cut yourself, if if it were liquid water that fills your cells, the water would come pouring out like a breached water pipe. The water comes, but it doesn't happen. Blood comes out certainly, but the water stays in. The water is kind of gel-like, viscous, and it sticks to the solids inside the cells. So if you
Right.
cut yourself, you don't. The water doesn't come pouring out.
But
Please.
can't we advance an argument there? Uh, I'm just trying to uh, reason here. So maybe the water doesn't come pouring out because of the cell walls. I mean, when we rupture, only a few select cells are broken, but not the rest. Could that also be a reason? Or
Well, yeah, it could be, but if you cut, you basically destroy it's not just cutting through the cell membrane, but the stress or strain that you put on all of the cells is going to rip them apart.
right,
Uh,
right,
yeah, I mean you have a point. Maybe that result is not as definitive, but I've spoken to surgeons, and they tell me during surgery they'll cut right through a muscle, and the water doesn't come pouring out. And the muscle contains it's a bundle of long cells, and you cut right through it. You'd expect that from both sides the water would come pouring out, but it doesn't. It doesn't come pouring out.
right,
Uh, and 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 you can do the same thing in the laboratory. You can take a long muscle cell and slice it, as you slice a sausage, and the water doesn't come out. So it's a different kind of water. Anyway,
right.
I saw scientific evidence from Gilbert Ling and from other scientists internationally, and I was intrigued. So I came back to Seattle. This was in Hungary. Came back to Seattle, and I wanted to reassure myself that I was not going nuts or going crazy. So I gave one of his books to some of my students, students who could really understand this, and each and every one of them came back to me and said, "This is really amazing." They hadn't known about it. They said, "If this guy is right, all of biology is wrong." And it looks like he's got the goods. He's got the evidence on it. And so first thing I did was to write a book. And the book is called Cells, Gels, and the Engines of Life. And the main purpose of the book was to try to illustrate the concepts that were brought forth by Gilbert Ling. And unfortunately, Gilbert Ling, as creative and as brilliant a scientist he was, his writing style was not very good, not clear. He'd sit down first at the typewriter and later at the word processor. He'd bat out something and he'd send it to the publisher and it would be published. No editing. He never heard. I think the word editing was not in his vocabulary. Maybe in Chinese there's no word for editing. I'm not sure, but
And
he
and how
never.
long ago? Sorry, and how long ago was this? How many years ago?
Well, I think his first book was like in the 70s,
Okay,
and by the time he passed, he'd written I think 6 or 7 books,
okay.
and
I was just
so
trying to figure out how long this has been known, and mainstream science has still not failed to catch up. Like if a
well,
discovery has been known for.
mainstream science has still not caught up, but it's really beginning to shift. I'll explain that in some moments, but he started. Well, we can we can do some arithmetic. I mean, he died several years ago at age 100 or so, and he came here at age roughly 25 or so, and it didn't take more than a decade before he started producing. So, if you do the
Yeah.
arithmetic, which I don't like to do online because I'll screw up. Um, but at any rate, he's been around
That's
for a while.
refreshing candor from a professor.
Oh well, I I try to be straight and honest. As a scientist, we're in search of truth, and well, at any rate, so these students they came back to me, and 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 they were really enthusiastic, and so step one was was we had to do experiments after the book was published, and the book was received with mixed reviews. Not some reviews said, "Oh, this is just more of Gilbert Ling," and we all know that Gilbert Ling is a crackpot. So pay no attention to this. It's just complete nonsense. At the other end of the spectrum was my favorite one was a review from a well-known cell biologist at Harvard University who said, and I quote, "This is a 304-page preface to the future of cell biology." That one I like better. um, yeah, well, um, so anyway, mixed reviews, and I wouldn't say that the book made tremendous impact, but it was supposed to be my gift to Gilbert Ling because I wanted to elucidate the principles, and I think at least the book it was clear, unlike Gilbert Ling, but Gilbert actually hated it, and he felt first that I kind of stole his thunder because I didn't mention the name Gilbert Ling in every sentence.
Okay.
Although it was really obvious that
Yeah.
that I thought I made it obvious that this is Gilbert Ling's idea, not my idea, and I was just explaining it and trying. And I went on in the book to suggest that if we start with Gilbert Ling's idea, we can go a step further in explaining a good deal of cell biology. Maybe that's the part that he didn't like, and he was really angry. It took me a decade to restore good relations with him when finally we could demonstrate this kind of long-range ordering experimentally in a really clear way. It was at a conference. He was sitting in the audience. I was speaking, and he just rose up and practically started applauding. This
Oh
is
wow.
fantastic evidence, and then we restored our friendship. I really tried because it's nuts, you have two people who are, you might say, revolting against the establishment point of view, and why should they be enemies? They
Yeah.
should be
Yeah.
friends.
Yeah. Yeah. You need all the
Well,
help you can get, and
yes, you need all the help you can get,
yeah.
and so that's when we started. And the first thing we did to get started was starting with Gilbert Ling's ideas, which, by the way, ultimately we found some issues, some problems, which led us on to some new thinking. The essential principle of long-range order is correct, I believe, but there are some notable differences, and those differences are really important, and that's what we wound up with calling this so-called structured water. We call it fourth phase water,
Right.
or
Right.
exclusion zone, EZ. You people, I think, say EZ. It doesn't
EZ.
work.
Yeah, in India, but
Is
yeah, we
that
can.
here?
Yeah.
EZ. It's easy to remember.
Yeah.
You
Yeah.
see, so it
Yeah.
worked very well here. But at any rate, we started doing experiments, and Gilbert Ling suggested his ideas. What he suggested, as you mentioned earlier, it's kind of like a crystal, and crystals are pure. To get something to crystallize, like for example water forming ice, if it's a pure crystal, it must divest itself of any contaminants that had been in the water. Just
Right.
get rid of them to get a
Right.
pure crystal, because it's not pure if it has contaminants. And so, as for example, as a glacier forms, you have the glacial moraine just beneath it. It pushes out
Yeah.
all the stuff and forms a pure crystal. And so we were looking for a situation with water in which particles, molecules were excluded, and that we could identify as structured water. And we found it quickly by dint of maybe good fortune or what have you. We found it, and so that's why we called it the exclusion zone, because it excluded. It was actually an idea that came from an Australian colleague. He said, you've done all these experiments and you show there's a region that's clear that has excluded all of the junk, all of the particles or molecules. Instead of describing it in so many words, just give it a name.
Mm-hmm.
Why not call it exclusion zone, or
Yeah.
easy
Yeah.
to remember?
Yeah.
And we did. And that was early on, and the name stuck. But I think it's not an appropriate name, because we found that this water, this kind of water, every measurement we made of this water showed that this water was completely different from ordinary liquid water.
Right.
And
just
therefore,
just to interrupt you, just for the sake of the viewers, so this is all away. I remember reading this book called The Fourth Phase of Water,
yeah,
which has extensive details about the studies conducted on this phase of water, the easy
Yes.
or the exclusion zone. So if anybody's interested, you can check out the book, The Fourth Phase of Water.
so we started studying, and so we found that next to all you need, what we found to build this kind of water, you need a surface, a material, and a surface, that material that's so-called hydrophilic, water-loving. It means that if you have a surface and you drop the water on it, the water spreads out instead of beating up as
Right.
it would on, say, Teflon or something like this. If you have that, then in most, not all cases, in most cases, this easy water builds. And it builds one layer at a time. And the layers have a hexagonal motif. Hexagons are so common in biology.
Almost like a
Uh,
cross section of a beehive, like
Yeah,
sliced
yeah.
beehives stacked
Yeah,
on one.
yeah, yeah. It's exactly right. That's what it looks like. So the hydrophilic surface sitting next to water, ordinary liquid water, the hydrophilic surface serves as a template for the growth of one sheet-like hexagonal layer, and then that hexagonal layer serves as the template for the growth of the next sheet, and the next, and the next, and the next, and these sheet-like layers grow one by one, and they grow to, in some cases, hundreds of thousands of layers,
Right.
enormous distances.
And does the structure, the nature of the structure of the hexagon, for example, does it change at all depending on the nature of the surface? Like if it's like a biological surface or inside a cell or on a tree or something else, depending on the surface with which the water is interacting, or is it independent of the?
No, it's not independent. So what I told you is kind of like a template.
Okay.
Well, sorry, it's a generic structure.
Okay.
But that generic structure, it appears to change, and the way it can change is that, the elements that build that structure are hydrogen and oxygen. That's all there is in water.
Yeah.
But arranged in a hexagonal fashion, and it turns out that oxygen has many different states, so-called oxidation states, and the one that's most familiar is the oxidation state -2. We call that the valence. But also, if you can read in chemistry textbooks, this is standard material. Not only -2, but it has -1, 0, +1, +2. And you can imagine if the oxygens in this stacked array of hexagons, if the oxygens, some of them take on -2, or some of them are -1 or 0, it means the precise structure can change.
Okay.
And so far the evidence is it does change, and it depends on the nature of the nucleating surface, of the
Okay.
hydrophilic surface. So, for example, the easy water, fourth phase water that's in your kidneys, its structure may differ somewhat from the water that's in your liver, et cetera, et cetera. Variance on a central theme.
And with this difference in structure may come difference in function, do you think, or difference in properties, or the role they play in a biological setting?
You know, when the cell functions, this is what we found. When the cell functions, the only way it functions is if this easy water, fourth phase water, undergoes a transition to ordinary liquid water and then goes back again. So, for example, in the contraction of muscle, you have the muscle proteins, and then the water will be essentially all fourth phase or easy water. But nothing can happen. It's like a block of ice. And
Yeah.
if you want something to happen, then there needs to be a change. And the change is called a phase change.
Right.
And what happens is the change occurs in the water and the macromolecules, mostly the proteins that are sitting inside the cell. The proteins in the water change together. And that's, in the case of muscle contraction, for example, that's what creates the contraction. The water changes and the muscles go from their extended state to their contracted state. And that's what contracts the muscle, unlike the theory that I mentioned earlier. And it's the same thing with secretory cells, for example. To secrete something, if the cell is not doing its job, not secreting, all the proteins in the water, proteins are extended and the water is in this structured easy form. But if the cell gets the message to secrete, everything changes, undergoes a phase change. The water becomes unstructured, it becomes liquid water, and the proteins undergo a change, and that's what spews out.
Right.
So same thing we surmise is occurring in all cells. To get the cell to work, the cell needs to undergo this phase change, and then it returns back again. That doesn't answer your question, but it provides a little bit of background that
Right.
maybe is relevant to your question.
But it does.
requires-
It does. Sorry, it does
Please.
trigger another question in my mind, because since we are on the subject of phase change, and since since we are treating easy water as the fourth phase, as you say, so in my understanding, like we all studied in school, traditionally there are three phases, right? Like the solid and of ice, and liquid, that is water, and steam, the gaseous state. So in my mind, these phases can exist independent of each other, like a block of ice can exist independent of steam or water.
Yeah.
But doesn't easy water depend on liquid water to exist? Like, or can you just have a beaker of easy water? So in that sense, is that a true by definition a true phase, or is it like a hyphenated phase that comes with a liquid phase?
Well, it doesn't necessarily come with the liquid phase. It's not liquid. It's like it has a consistency of raw egg white, for example.
Okay.
Now, would you consider that to be a liquid or a solid? There are lots of gel-like substances. Is that a liquid or is it a solid? I ask you. It's not so clear.
Right. Yeah. Yeah.
Yeah, and so maybe we're not justified in calling this a phase, but I think it's different from a solid. It's different from a liquid, and
Right.
maybe the idea of three phases is not correct.
Right. Yeah.
We have a tendency to assume that whatever's been in the textbook for a few generations is correct. It must be correct because otherwise it wouldn't be in the textbooks.
Right.
But if you think about how textbooks are written and published, you quickly can understand that textbooks, radical ideas don't exist in textbooks because textbook publisher wants to sell.
Yeah. Yeah.
And,
And there's a standard curriculum to follow.
Yeah, it's got to present the standard material.
Yeah,
So even if the publisher thinks, oh, I think it's maybe not quite right, I've read about some revolutionary ideas, they won't put it in the book because
Yeah.
it won't sell.
Yeah.
And so it's ideas are then perpetuated. So here's an example that I've been working on. I don't want to digress too much, but I'm working on a book that has to do with the structure of the atom. Now we presume that the atomic structure, it's since Niels Bohr came out with the idea of a solar system like model. So you've got a nucleus, protons and neutrons, and then you have surrounded by electrons. And that's been modified by quantum mechanical considerations, but essentially you still have a nucleus and electrons. And if you think about it, there's some real problems that arise, and these are not problems that only PhDs in abstract mathematics can understand. They're middle school principles. So, for example, the nucleus has neutrons and protons. Protons are positively charged, neutrons are neutral. Now, when you lump all of these positive charges together into a closed space, what do they want to do? Well, positive charges repel one another, and so in theory the nucleus should explode.
Right.
Now, the physicists have addressed this problem. They've postulated a force is a kind of glue that holds it together. It's called the strong force. As far as I can see, there's no independent evidence for a strong force. It's just a necessary condition to hold it together. Otherwise, the model blows up.
Right.
And so if you think that's not enough, then think about this. In middle school, I learned that minus and plus attract one another. And I'm sure you learned the same thing.
Yeah.
So you've got a nucleus that's positive, and you have electrons that surround it that are negative. So, if I'm a middle school student, I'm going to ask my teacher, well, wait a second, if the electrons are negative, won't they be attracted to the positive nucleus? And won't the atom collapse into nothing?
Yeah.
I've seen no answer to this very simple question. So I'm just giving that as an example of, even at the most fundamental level, you can think of what we've come to accept. Everybody accepts because they've been in the textbook for 5-6 generations. We presume it must be true, but these very simple considerations lead to questions and head scratching. There's something wrong here. How come nobody's talking about it?
Yeah, it's very interesting because it's almost as if we make certain assumptions at each stage, and downstream, down the years down the line, we just forgot that there were assumptions made and theories built on that, and there was never any direct evidence for it.
Absolutely, you got it. Yeah, you hit the nail exactly on the head, and we're talking about considerations at the most fundamental level. So, and I guess since I've done science for quite a few decades, I guess I reserve the right to develop a philosophy. And my philosophy is very simple. Mother Nature works in simple ways. And if the mechanism that you're considering or reading about is complicated, it's probably not true.
Right.
This is not my idea. It starts with Sir William of Occam.
Yeah, the Occam's razor.
Principle. Occam's razor, right? And a few hundred years later, he was a friar in a church. He was involved in somehow in the church, and he was talking about the existence of God. And he said, well, look, there are two possibilities. God exists, God doesn't exist. How are we going to find out? He said, well, there are two hypotheses. God exists, God doesn't exist. And the way you can decide which one is correct is it's got to be the simpler one.
Right.
Simpler one.
Yeah.
And then 300, I think, years later, Isaac Newton thought, this is a cool idea. I think it should apply as well to science and scientific thinking. So it became known, as you say, as Occam's razor.
Yeah.
And for many years, that principle dominated science. It's got to be simple.
Yeah.
Until about 100 years ago, um, when the idea of quantum mechanics and basically abstract mathematics began to dominate, and then that principle has kind of um, uh, retreated to the background.
Right.
And a lot of people now are thinking, well, it's really complex. Complexity that prevails, not simplicity. I guess since I've done science for quite a few years, I'm entitled to an opinion, and I think Occam's razor is correct, and that nature operates on the principle of simplicity.
Right.
And if it looks complicated, it could be that you're not smart enough to figure it out, but it could also be that it's wrong.
Okay, so we have about 20 minutes left. So before we go to the implications and applications of easy water, I just want to quickly ask: is this a phenomenon exclusive to water, or have you? Is it all polar liquids, or all aqueous solutions, or all?
I can't say all because we haven't studied all. We studied some, and everyone we studied showed pretty much the same. I was really seriously disappointed because I thought I'd learned, and I thought that water was unique, and that, for example, in order to create life, you must have water.
Right.
I'm not so sure now because, I think this fourth phase of water, which fills our cells,
Right.
is critically important for life. But, excuse me, it's possible, it's possible that some other polar molecule can substitute, like, for example, ethanol. It also forms exclusion zones, and we were surprised, and as I said, ultimately disappointed, but facts are facts.
Right. Coming to how the structured water affects life and its presence in cells. One of my pet theories, you can say, about, for example, blood circulation. What I've read about something very interesting is how the heart is not actually a pump, and people assume that heart is just a mechanical pump, but they argue that the RBC and the WBC, the cells, are just they're just way too big for the capillaries to propagate all the way to the cells and come back purely because of the pumping action. And some scientists propose some kind of a vortex means of propulsion where the blood cells stick to the center of the tube, avoiding the walls. And I don't remember all the details of the theory, but do you think there is a role of easy water here in blood propagation through blood vessels?
Yes. Well, my first comment is I really can't understand the argument that the heart is not a pump, because you can measure the pressure that's developed. When the heart contracts, you can measure the pressure in the ventricle or just beyond the artery, and it builds to a high pressure. And it seems to me that that's exactly what happens in a pump. And so I have read or heard about the ideas that there's a vortex that forms, but everything beyond that has always seemed vague to me.
Right.
Now, so that's one side of the story. The other side of the story is that we found that the vessels themselves are fundamentally involved in propelling the blood. So, for example, we start with observations that made by us and by half dozen other laboratories over the past 100 years or so. You stop the heart, and you would say, well, if you stop the heart, the flow will cease, right?
Yeah.
That's what everybody thinks, but it's not the case. If you stop the heart, now more than a half dozen independent reports and different biological systems, different animals, show that the blood keeps going, and not for a few milliseconds or something, for over the long term. And we found exactly the same. So, what's the interpretation of that? Either it's some artifact, which could be, although, as I said, now more than a half dozen different laboratories under different circumstances show the same thing, or there's something beyond the heart that's also driving the blood. And I found out about this. I got interested in the subject when I went to Moscow to visit my friend Vladimir Vyakov at Moscow University. He's the vice chair of biochemistry there. And he said, after some vodka and such the evening before, he said.
Speaking of which, does vodka have an exclusion zone?
Well, the ethanol, indeed, and I know that Mendeleev, the guy who was responsible, for the periodic table, was actually very much deeply involved in figuring out what's the optimum ratio of water and alcohol for vodka, and he discovered it. So that's a side issue. Anyway, so this guy, I met this Russian guy in the next laboratory, and he starts telling me about there's something fundamentally problematic about the cardiovascular system, about our understanding. And I'm standing there with some degree of arrogance because I studied pressures and flows in the cardiovascular system for my PhD, and I thought we had it all worked out and all understood. In 5 minutes, he had me convinced that I was wrong and that there was something fundamentally wrong with our concept. Why is that? Mm-hmm. He said, well, the red blood cells, the diameter is 6 or 7 micrometers. The capillaries are as small as 3 or 4 micrometers. So you've got a plumbing problem. Yeah. How do you squeeze this big bolus into the narrow capillaries? Right. And the way you do it is you bend each red blood cell in order to allow it to go through the capillaries. To do that requires energy. And he did a calculation, the Russians are big on calculations, and he said if the ventricle alone were responsible for this, the pressure that it would need to develop in order to achieve this bending, which you can actually see on videos, it's not theoretical, he said the heart would need to develop something like 1 million times the pressure that it ordinarily develops. If that's not high blood pressure, I don't know what is. Yeah. So obviously, unless his calculation is way, way off, there's a real problem in the cardiovascular system. Right. There needs to be some but supplementary or complementary source to drive the flow. Right. Meanwhile, I'm scratching my head, and you can see that's why I'm missing, a lot of hair. And thinking we had just found something in the laboratory. We take a tube, a hydrophilic tube, horizontally, put it in water, and the flow goes perpetually right through it, like through a straw. It keeps going, but there's no pressure gradient or anything like that to drive the flow through. Right. Something else is going on, and we eventually found inside the tube is an exclusion zone, which is negatively charged, and we know that whenever you get this negatively charged zone, you get positive charges, complementary positive charges that exist just beyond that zone, because they have to add up to neutrality. You're starting with neutral water, right. And from the neutral water, you're producing EZ water, and you have to produce protons also, because minus and plus have to add up to 0. Right. That's what you started with. So it happens inside these tubes. You have a EZ, an annular EZ, just inside the wall of the tube, and you've got protons at the center. And the protons start building up, they repel each other, and they want to get out. Right. They're free. Right. They go this way or they go this way. So we already had several papers on this. We understand the principles pretty well. And I'm thinking maybe the same thing happens in the cardiovascular system. What we saw in terms of these tubes, maybe the same principle exists inside blood vessels. Right. Tubes, hydrophilic tubes. Please.
Yeah, sorry. So, and a related question, since we are on the subject. propagation of water against gravity in trees. I think this is another thing you mentioned in your book. Uh,
Yes,
so easy water also plays a role in where the water climbs to the top of really tall
yes,
trees,
yes.
which can't be
Same thing.
explained by just
The
capillarity.
repulsive force, right? You got easy water, and then you have the protons that are free in the bulk water, and these protons repel each other, and you know you have to understand or figure out how water can reach 100 meters. The redwood trees in California,
Right.
and water doesn't want to pile up that way.
Right.
But if you've got the pressure of these protons pushing, then that's another story.
Right.
So yes, absolutely, that's true. So
And
yeah,
and I had a few more. Actually, I had quite a few points to ask, but I don't think we'll have the time to cover all of them. But one question before we go to the concluding portion is one of my one of the topics I'm fascinated by is homeopathy. Water memory. Apparently, homeopathy is based on this principle that water retains information about particles that were dissolved in it. So, what do you think about it?
oh, I think it's true, and I think we now understand the mechanism. First of all, homeopathy is um, evokes a mixture of feelings, thoughts, whatever among people. Some say this is preposterous. On the other hand, it works. It seems to work. Even works on animals, where the placebo effect you wouldn't expect. I know some veterinary homeopaths who have been in business for many years, and people keep coming back because it seems to work. And so yeah, there is the question of if you undergo these dilutions to serial dilutions that effectively ensure that there are none of the original molecules left, at least statistically, only water. How possibly can water somehow retain the memory? And I think the principle is the easy water principle. So the critical aspect, which has been actually demonstrated by a well-known Russian scientist, is you must succuss, shake. So when they do the dilution, for each dilution, they shake it like this or mechanically now. And if easy has been built up, we found that agitation breaks up the easy into a lot of little easies. So if you can imagine that easy has built in some way next to the original molecules that were in there, and this easy retains information from those molecules against which it were sitting, and then you shake it, and if you shake it, this easy containing information is broken up into 1,000 little easies, and so you do the next dilution. Some of those little easies, mini easies, are going to be transferred to the solution, and this repeats itself again and again, and therefore, because each time you do the dilution, you're breaking up an easy into a lot of little ones. The little ones are included, so the information will be perpetually included.
Yeah, and this is really fascinating for me because this evokes the idea of a hologram, because the information as a hologram, you break it down, and each particle, even as you reduce, it's not destroyed, but each one retains the information about the whole somehow.
Well, yeah, I see the similarity between the two. Yeah, but well, yeah, homeopathy, it remains partly a political issue because, it challenges some of what the pharmaceutical companies are producing, and I don't like it, and
Yeah.
and so there's basically a war that's being waged against homeopathy.
Right.
It's a pity because it seems to work,
Yeah.
and well, I think we're beginning to understand the principles. Um, so yeah, does that answer your
Oh yeah, yeah,
question?
yeah. And finally, as we conclude, what do you think is the future of water research? Are you happy with where it is going, or would you, what are you actively still involved in guiding students in this research, or has it come to a
Yeah.
stop?
Well, we have a laboratory, and laboratory is still going. It's not easy for us to raise money, and in order to have a very active laboratory, which I've had all my career. An active laboratory means 7, 8, 9, 10 people, students and postdocs working, each with different background and different contributions, which really helps. If you got a problem in one area, like an electrical problem, it's nice to have someone present who has experience in electrical engineering, for example, et cetera, et cetera. So it's really difficult to get money for anybody who has an alternative idea from the funding institutions, because the way the reviews are set up, it's the establishment people who are doing the reviewing, and those are the very people you're challenging.
Yeah,
And
yeah.
so,
There's so much
you know,
vested interest in research.
yes, absolutely, absolutely. You have to toe the line in order to get money,
Right.
and we don't toe the line, so it's been difficult. So we've depended on private funding, and we had a funder for I think 6 or 7 years, who was amply funding the laboratory. Unfortunately, although he wanted to fund us indefinitely, he ran into some financial difficulties and he had to withdraw. And we're now funded by a foundation to do very specific kind of research, but it's modest funding, and we need more. We need somewhere between $500,000 and $1 million US dollars per year to run a laboratory. It's been a challenge to get that money. There are so many exciting things that are going on, well beyond biology, and unfortunately, it takes money to run. The university doesn't supply anything. They like to take money. They don't supply money.
Right.
So
Right.
if you get, for example, money from the National Institutes of Health, they'll take a 50%, they'll take an extra 50%
Wow.
from NIH to cover the cost of toilet paper and lights and whatever.
Wow. Wow.
So it's a difficult position if you're challenging the establishment point of view in any way. It becomes a real challenge to get money, and that's why if I were to ask you, for example, if you could name a scientific revolution that's occurred in the past, say, 30 or 40 years, I mean scientific, not a technological revolution,
Right. Like in theoretical
like
science.
a laptop computer. Scientific, you'd be hard pressed to find one that's of the same significance, say, as splitting of the atom or the founding of the genetic code. The latter is, let's say, 65 years ago, and the splitting of the atom was maybe 75 or 80 years ago.
Right.
And why is it that there are very few scientific revolutions? Well, it's because anybody with a revolutionary idea finds it very difficult to get funding. So, I'm sorry, long answer to your short
No,
question.
no, it's. I think it's a very important, very critical point to highlight, because it's the state of research in the universities around the world, how they are so dependent on the people who fund and the people who have their own agendas to push.
Yes.
So finally, do you have any other books coming out?
I have 2 books coming out.
Okay.
One of them, it just depends on the artist, who is my son, who has been busy remodeling his home for the past 3.5 years, and so we're delayed. But now he's back at work, and the first of the 2 books deals with it's called Charged. If I can remember the exact title, the unsuspectedly profound role of electrical charge in nature. And the book deals with everyday phenomena, and that we think we understand, we don't really understand them. And if you actually invoke electrical charges, you can begin to really understand what's going on.
Right.
An example is weather. I spent 4 chapters on weather. If you try to understand, looking at a textbook or the internet or whatever, the principles, the first principles underlying weather, starting with evaporation, for example, cloud formation, and such. You won't find anything that starts from first principles and builds up.
Right.
I present that in the book,
Right.
along with issues like what turns the Earth every 24 hours, what's responsible for atmospheric pressure, how do birds fly, among other things. So
Right.
that's in that book. And the one beyond deals with what I was alluding to earlier about the structure of the atom. I think we got it wrong. And I'm proposing another model that is actually, I found out, is amazingly similar to what the chemists proposed 100 years ago, because they didn't like the model that I was talking about, that we all know, that the physicists came out with. But it was, it was the era of physics, so the physicists dominated. But the chemists didn't like it. One of the most prominent chemists said, your model, this solar system-like model, doesn't explain even the simplest of chemical reactions.
Right.
So that's the second book.
book. Okay. Okay.
Yeah.
So
I'm excited.
Mhm.
Yeah.
Okay, so with that, I think I'm afraid we have to close. I mean, I would have loved to have had a chat with you about a lot more topics that I had written down, but perhaps another time. So thank you so much for joining and talking.
Well, and thank you for the opportunity. Much appreciated.
Thank you so much. Thank you so much, and I wish you all the best for your books and future research, sir.
Well, and thank you for your astute questions.
Thank you. Thanks.
Which I appreciate.